Just a second, everyone. I'm just doing some sound testing. I want to listen to this audiobook. It's by Stephen Hawking. It's called A Brief History of Time. And then I want to comment on it too, but I really wanted to get into this is like a basic book. Like if you were getting I was gonna do the 48 laws of power, but I decided not to. On it too, but I really wanted to get into this is like an introduction to science kind of book. Like this is Stephen Hawking. So let's start it. I'm gonna talk through it. I'm gonna take breaks and have tangents and stuff like that. But yeah, let's get into it.
We go about our daily lives understanding almost nothing of the world. We give little thought to the machinery that generates the sunlight that makes life possible, to the gravity that glues us to an Earth that would otherwise send us spinning off into space, or to the atoms of which we're made and on whose stability we fundamentally depend. Except for children who don't know enough not to ask the important questions, few of us spend much time wondering why nature is the way it is, where the cosmos came from, or whether it was always there. If time will one day flow backward, and effects precede causes, or whether there are ultimate limits to what humans can know. There are even children, and I have met some of them, who want to know what a black hole looks like. What is the smallest piece of matter? Why we remember the past and not the future? How it is, if there was chaos early, that there is apparently order today, and why there is a universe. In our society, it is still customary for parents and teachers to answer most of these questions with a shrug or with an appeal to vaguely recalled religious precepts. Some are uncomfortable with issues like these because they so vividly expose the limitations of human understanding. But much of philosophy and science has been driven by such inquiries. An increasing number of adults are willing to ask questions of this sort, and occasionally they get some astonishing answers. Equidistant from the atoms and the stars, we are expanding our exploratory horizons to embrace both the very small and the very large. In the spring of 1974, about 2 years...
Okay, guys. So pretty much it's just talking about how different attributes and stuff. We really didn't get into it. We're gonna get more into it, but yeah, let's keep going. I just wanted to say I'm gonna take breaks. I should turn this down. I am listening, by the way. I am listening to the audiobook, so take that for what you will. I just want to get this in my head as soon as possible.
Before the Viking spacecraft landed on Mars, I was at a meeting in England sponsored by the Royal Society of London to explore the question of how to search for extraterrestrial life. During a coffee break, I noticed that a much larger meeting was being held in an adjacent hall, which, out of curiosity, I entered. I soon realized that I was witnessing an ancient rite, the investiture of new fellows into the Royal Society, one of the most ancient scholarly organizations on the planet. In the front row, a young man in a wheelchair was very slowly signing his name in a book that bore on its earliest pages the signature of Isaac Newton. When at last he finished, there was a stirring ovation. Stephen Hawking was a legend even then. Hawking is now the Lucasian Professor of Mathematics at Cambridge University, a post once held by Newton and later by P.A.M. Dirac, two celebrated explorers of the very large and the very small. He is their worthy successor. This, Hawking's first book for the non-specialist, holds rewards of many kinds for the lay audience. As interesting as the book's wide-ranging contents is, the glimpse it provides into the workings of the author's mind. In this book are lucid revelations on the frontiers of physics, astronomy, cosmology, and courage. This is also a book about God, or perhaps about the absence of God. The word God fills these pages. Hawking embarks on a quest to answer Einstein's famous question about whether God had any choice in creating the universe. Hawking is attempting, as he explicitly states, to understand the mind of God. And this makes all the more unexpected the conclusion of the effort, at least so far. A universe with no edge in space, no beginning or end in time, and nothing for a creator to do. Carl Sagan, Cornell University, Ithaca, New York. Chapter 1. Our Picture of the Universe. A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the Sun, and how the Sun, in turn, orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you've told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise." The scientist gave a superior smile before replying, "What is the tortoise standing on?" "You're very clever, young man, very clever. But it's turtles all the way down." Most people would find the picture of our universe as an infinite tower of tortoises rather ridiculous. But why do we think we know better? What do we know about the universe? And how do we know it? Where did the universe come from?
In other words, Stephen Hawking, I think this is Carl Sagan talking right now for the introduction of this book. But essentially what he's saying is the world isn't flat. People used to think that the world was flat and that, you know, this and that and this and that. The world is not flat. It is not flat. You could look at shadows, you could look at just basic gravity. Basic gravity will show you the world is not flat. Right? So this is a common misconception now in the 20th modern 21st century, that so many people think that the earth is flat and all this. Let me tell you something. I've had magical dreams of places you wouldn't even believe existed. I can tell you the earth isn't flat. I'm just flat out tell you right now. Like I've had dreams, like magical dreams, like dreams that you would see in Skyrim. Right? Hey, Happy Hoons. I've had dreams that you would see in Skyrim, like of like incredible places. But I can still rest assured tell you that the world isn't flat. I can tell you 100% without a doubt. Hello, Happy Hoons, how's it going? I'm just playing this game. I don't know how to get the bit rate up. Yeah, flat out, the earth isn't flat. I'm telling you guys the truth. Anyone who tries to tell you otherwise, don't listen to them. They're feeding you nonsense. They're conspiracy theorists. They think in a different way than reality. They're so caught up in in all of the fantasy. What they're really thinking about is like fantasy, like men in the Othello book. Those they're thinking about medieval creatures, right? They're thinking about, you know that's all fantasy, though. In reality, it's
I know this
animals. It's
place.
not
We
mythical
made our last
creatures.
stand here many years ago. Gone. Why am I here?
I know what you're saying. I can see the world myself, but even it is, who gives a damn? Yeah, exactly. Exactly. But the earth isn't flat. One time in the seventh grade, God bless my seventh grade teacher, by the way. But there was a substitute teacher that came into the classroom, and he tried convincing us all that dinosaurs were still around, like dinosaurs. And he was trying to tell us that, like, these giant dinosaurs were around in South America, and the whole history textbook is a lie, and he was really doing this. And the next day, my science teacher was so mad. Oh my goodness, I could see how mad he was. And honestly, I was a kid and I could see how mad he was. And he picked up the science textbook and he said, this. He picked up the science
Wait.
textbook and he said, this is fact. Everything that you heard from the man before, it's absolute false fiction. There are no dinosaurs. They're all extinct. Right? You could kind of tell that that substitute teacher was a little autistic. Little undiagnosed autism, but that's not a bad thing. I'm just saying, that's how it was, right? So, the earth isn't flat. And people will do anything to make you believe in bullshit. All right, guys. Yeah, well, the Bible does work in metaphors. The earth isn't flat. I believe in a cosmic heaven. Did you know that, Happy Hoons? I believe that your soul can travel planets and live on different planets. That's partly why I'm gonna be buried that's partly why I have a specific burial. It's because I believe I'll do the same exact thing somewhere else. You guys kind of know what I mean? I'm not saying I'm gonna cease anytime soon. I'm just saying, it's that important to me. It's kind of like Morgan Freeman with his earrings, which, by the way, bless Morgan Freeman to high heaven. But anyway, let's get back into it. Which, by the way, I love hearing Morgan Freeman narrate science documentaries. You guys know? Oh, that's an interesting thought, Happy Hoons. We are the atoms inside. That's so interesting. That's so interesting. Then all glory to God, right? All glory to God. But let's get back into a brief history of time.
And where's it going? Did the universe have a beginning? And if so, What happened before then? What is the nature of time? Will it ever come to an end? Recent breakthroughs in physics, made possible in part by fantastic new technologies, suggest answers to some of these long-standing questions. Someday, these answers may seem as obvious to us on Earth as the Earth is orbiting the Sun, or perhaps as ridiculous as the Tower of Tortoises. Only time, whatever that may be, will tell. As long ago as 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the Earth was a round sphere rather than a flat plate.
I got a
He
monster.
realized that eclipses of the moon
Look.
were caused by the Earth coming between the sun and the moon. The Earth's shadow on the moon was always round, which would be true only if the Earth was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the eclipse always occurred at a time when the sun was directly under the center of the disk. Second, the Greeks knew from their travels that the North Star appeared lower in the sky when viewed in the south than it did in more northerly regions. Since the North Star lies over the North Pole, it appears to be directly above an observer at the North Pole. But to someone looking from the equator, it appears to lie just at the horizon. From the difference in the apparent position of the North Star in Egypt and Greece, Aristotle even quoted an estimate that the distance around the Earth was 400,000 stadia. Now, it's not known exactly what length a stadium was, but it may have been about 200 yards, which would make Aristotle's estimate about twice the currently accepted figure. The Greeks even had a third argument that the Earth must be round, for why else does one first see the sails of a ship coming over the horizon and only later see the hull? Aristotle thought that the Earth was stationary and that the sun, the moon, the planets, and the stars moved in circular orbits about the Earth. He believed this because he felt, for mystical reasons, that the Earth was the center of the universe, and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 2nd century AD in a complete cosmological model. The Earth stood at the center, surrounded by 8 spheres that carried the moon, the sun, the stars, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves moved on smaller circles attached to their respective spheres in order to account for their rather complicated observed paths in the sky. The outermost sphere carried the so-called fixed stars, which always stay in the same position relative to each other, but which rotate together
I'm
across
just
the sky.
listening to the audiobook right
What
now.
lay beyond the last sphere was never made very clear, but it certainly was not part of mankind's observable universe. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a path that sometimes brought it twice as close to the Earth as at other times. And that meant that the moon ought sometimes to appear twice as big as at other times. Ptolemy recognized this flaw, but nevertheless his model was generally, although not universally, accepted. It was adopted by the Christian Church as the picture of the universe that was in accordance with Scripture, for it had the great advantage that it left lots of room outside the sphere of fixed stars for heaven and hell. A simpler model was proposed in the year 1514 by a Polish priest, Nicholas Copernicus.
Hi, Troy. How's it going, buddy? My day was good. My day was good. I'm just doing I'm just listening to this audio book, A Brief History of Time, and I'm enjoying it. I think I'm gonna do this more often. But pretty much what I'm getting from this is that the Greeks noticed the moon changed, and the Greeks knew a lot about the moon way back in the day. And if the Earth was flat, the moon would be elongated and oval shaped rather than round. You got to keep in mind the moon is round too. Oh shoot, these guys are gonna be the death of me. No, I can't die. Oh. Okay, I got it. Thank goodness I had that. Time is a fallacy, a human-created construct, abstract in nature like numbers, alphabet, language. These are tools. Yeah, I understand what you're saying. Time is different for everybody. Sure is. Time sure is different for everybody. You could be old and yeah, you could be old and it could be very difficult for you to comprehend time, especially in your golden years. Time goes by really quickly, and then you just have to accept it. You just have to accept it. But I believe in an afterlife. I believe in other planets. I believe there's different planets out there that are in different time areas and different times in different time periods. Like there's some, I don't know, you got to think like science fiction. You got to think like Star Trek. That's what Stephen Hawking would want you to do. Stephen Hawking would want you to think outside the box. What could be? You know, and by the way, I never completely, in the entertainment industry, I never complain about anything. I think of Stephen Hawking's suffering before I ever complain about anything that I have to deal with. What is done is no more. What's to come is unpredictable. Now it doesn't exist. My alarm clock disagrees. Yeah, guys, it is what it is. But anyway, let's get back into it. The Greeks knew about the moon for a long time. The Greeks knew the Earth wasn't flat.
At first, perhaps for fear of being branded a heretic by his church, Copernicus circulated his model anonymously. His idea was that the sun was stationary at the center and that the Earth and the planets moved in circular orbits around the sun. Nearly a century passed before this idea was taken seriously. Then two astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly to support the Copernican theory, despite the fact that the orbits it predicted did not quite match the ones observed. The death blow to the Aristotelian Ptolemaic theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons that orbited around it. This implied that everything did not have to orbit directly around the Earth, as Aristotle and Ptolemy had thought. It was, of course, still possible to believe that the Earth was stationary at the center of the universe and that the moons of Jupiter moved on extremely complicated paths around the Earth, giving the appearance that they orbited Jupiter. However, Copernicus's theory was much simpler. At the same time, Johannes Kepler had modified Copernicus's theory, suggesting that the planets moved not in circles, but in ellipses. An ellipse is an elongated circle. The predictions now finally matched the observations. As far as Kepler was concerned, elliptical orbits were merely an ad hoc hypothesis, and a rather repugnant one at that, because ellipses were clearly less perfect than circles. Having discovered almost by accident that elliptical orbits fit the observations well, he could not reconcile them with his idea that the planets were made to orbit the sun by magnetic forces. An explanation was provided only much later, in 1687, when Sir Isaac Newton published his Philosophiae Naturalis Principia Mathematica, probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies move in space and time, but he also developed the complicated mathematics needed to analyze the motions. In addition, Newton postulated a law of universal gravitation according to which each body in the universe was attracted toward every other body by a force that was stronger and more massive the bodies and the closer they were to each other. It was this same force that caused objects to fall to the ground. The story that Newton was inspired by an apple hitting his head is almost certainly apocryphal. All Newton himself ever said was that the idea of gravity came to him as he sat in contemplative mood and was occasioned by the fall of an apple. Newton went on to show that according to his law, gravity causes the moon to move in an elliptical orbit around the Earth and causes the Earth and the planets to follow elliptical paths around the sun. The Copernican model got rid of Ptolemy's celestial spheres, and with them the idea that the universe had a natural boundary. Since fixed stars did not appear to change their positions apart from a rotation across the sky caused by the Earth spinning on its axis, it became natural to suppose that the fixed stars were objects like our sun, but very much farther away. Newton realized that according to his theory of gravity, the stars should attract each other, so it seemed that they could not remain essentially motionless. Would they not fall all together at some point? In a letter in 1691 to Richard Bentley, another leading thinker of his day, Newton argued that this would indeed happen if there were only a finite number of stars distributed over a finite region of space. But he reasoned that if, on the other hand, there were an infinite number of stars distributed more or less uniformly over infinite space, this would not happen because there would not be any central point for them to fall to. This argument is an instance of the pitfalls that you can encounter in talking about infinity. In an infinite universe, every point can be regarded as the center because every point has an infinite number of stars on each side of it. The correct approach, it was realized only much later, is to consider the finite situation, in which the stars all fall in on each other, and then to ask how things change if one adds more stars roughly uniformly distributed outside this region. According to Newton's law, the extra stars would make no difference at all to the original ones on average, so the stars would fall in just as fast. We can add as many stars as we like, but they will always still collapse in on themselves. We now know it is impossible to have an infinite static model of the universe in which gravity is always attractive. It's an interesting reflection on the general climate of thought before the 20th century that no one had suggested that the universe was expanding or contracting. It was generally accepted that either the universe had existed forever in an unchanging state, or that it had been created at a finite time in the past, more or less as we observe it today. In part, this may have been due to people's tendency to believe in eternal truths, as well as the comfort they found in the thought that even though they may grow old and die, the universe is eternal and unchanging.
Wow, this is really getting into a brief history of time right off the bat. So he mentioned that children particularly are obsessed with black holes. Oh, you're hungry, Troy? You know, that's funny
Even those who
because I too am a black hole connoisseur. Black Hole Sun is a great song, by the way. I liken myself to the guy who feeds the goat milk. That's who I am in life. I feed the goat milk. So, I love that music video and album. I love Soundgarden and all of that. But yeah. you know, you keep doing what you're doing. He mentioned, which by the way, I'm quitting this game. He mentioned that even after death, the universe keeps going on, and it is a forever unending cycle between life and death and evolution in society and the food chain. Just a second, guys. Okay, I'm still right here. But yeah, so they're talking about how, just a second, guys. I'm gonna play Grand Theft Auto while we do this. I just have to get it windowed. But yeah, hello Nick. I'm just playing random video games. I just got finished playing ESL. I'm listening to A Brief History of Time audiobook and really taking it in. Stephen Hawking is amazing, and I never complain for my misfortunes because I know that Stephen Hawking had to deal with one of the ultimate health curses of being immobilized. And he still yet proceeded to make the world an incredible place. He left an incredible footprint. I always try to do good by Stephen Hawking. Oh, really? That'll be amazing. It would be. I love Maine. Maine is incredible. I want to do a meetup sometime for my fans who are interested in. Would you like to have dinner? Oh, would I ever? It's just I have no ride. I'll tell you what. I'll tell you what. I'll tell you what, Happy Hoons. When I make it big with my music and my movies and all of that, I promise I'll take you to dinner. Right? You just try to find me for real. I promise we'll do it all. We'll make a YouTube video. Just a second, guys. I'm trying. No. It's totally all right. It's totally all right. No. I know it's not a gay thing. Asian thing is way better anyway. By the way, I prefer Asian thing over many other thing. I'm just telling you the truth. Cause Asian thing doesn't try to take. You know? So yeah. Thank you so much. Ugh, sorry. Guys. I'm a complete egalitarian. I have to be careful what I say. It's just I've had experiences with people in the past, and I love anime and I love Asians. I love Mexicans too. I love Mexican food. All right, here we go. Display. I love Mexican and I love black soul food. I love black soul food. I love Cajun food. I love whatever Nana can cook. You know, I'm totally all for it. I have no problem. Just a second. All right, there we go. I fixed it. I just have to figure out how to control Alt Tab. All right, here we go. All right, game capture, properties. All right, there we go. Can you guys see that fat ad? Hello. Can you guys see that? Is it playing GTA? No, it's not. Okay, let's bring it back to GTA. Okay, there we go. We fixed it. Okay, so we talked enough about, growing old and how the universe keeps going and how there's an infinite amount of stars on every side of the planet. An infinite amount of stars, and the galaxy is never ending.
Realized that Newton's theory of gravity showed that the universe could not be static, did not think to suggest that it might be expanding. Instead, they attempted to modify the theory by making the gravitational force repulsive at very large distances. This did not significantly affect their predictions of the motions of the planets, but it allowed an infinite distribution of stars to remain in equilibrium, with the attractive forces between nearby stars balanced by the repulsive forces from those that were farther away. However, we now believe such an equilibrium would be unstable. If the stars in some region got only slightly nearer each other, the attractive forces between them would become stronger and dominate over the repulsive forces, so that the stars would continue to fall toward each other. On the other hand, if the stars got a bit farther away from each other, the repulsive forces would dominate and drive them farther apart. Another objection to an infinite static universe is normally ascribed to the German philosopher Heinrich Olbers, who wrote about the theory in 1823. In fact, various contemporaries of Newton had raised the problem, and the Olbers article was not even the first to contain plausible arguments against it. It was, however, the first to be widely noted. The difficulty is that in an infinite static universe, nearly every line of sight would end on the surface of a star. Thus, one would expect that the whole sky would be as bright as the sun, even at night. Albert's counter-argument was that the light from distant stars would be dimmed by absorption from intervening matter. However, if that happened, the intervening matter would eventually heat up until it glowed as brightly as the stars. The only way of avoiding the conclusion that the whole of the night sky should be as bright as the surface of the sun would be to assume that the stars
I
have
forgot
not
which
been
one it
shining
is.
forever, but had turned on at some finite time in the past. In that case, the absorbing matter might not have heated up yet, or the light from distant stars might not yet have reached us. And that brings us to the question of what could have caused the stars to have turned on in the first place. The beginning of the universe had, of course, been discussed long before this. According to a number of early cosmologies and the Jewish, Christian, Muslim tradition, the universe started at a finite and not very distant time in the past. One argument for such a beginning was the feeling that it was necessary to have first cause to explain the existence of the universe. Within the universe, you always explained one event as being caused by some earlier event, but the existence of the universe itself could be explained in this way only if it had some beginning. Another argument was put forward by St. Augustine in his book, The City of God. He pointed out that civilization is progressing, and we remember who performed this deed or developed that technique.
I
Thus
have
man,
to do this.
and so also perhaps the universe, could not
Just a
have been
second.
around all that long. St.
What
Augustine
is the mural
accepted the date of
gonna
about
be?
5000 BC for the creation of the universe according to the book of Genesis.
This
It's
one
interesting
reminds
that
me
this
of
is not
War, but
so
this
far
one
from the
has a
end of the
dog
last
on
ice
it,
age, about 10,000
and
BC,
that's
which is
dope.
when archaeologists tell us that civilization really began. Aristotle, and most of the other Greek philosophers, on the other hand, did not
There.
like the idea of a creation because it smacked too much
Oh
of divine
shoot, it's
intervention.
McTosh
They believed,
extra.
therefore, that the human race
Alright,
and the
I'm
world
happy
around
with
it
this.
had existed and would exist forever. The ancients had already considered the argument about progress described above and answered it by saying that there had been periodic floods or other disasters that repeatedly set the human race right back to the beginning of civilization. The questions of whether the universe had a beginning in time and whether it is limited in space were later extensively examined by the philosopher Immanuel Kant in his monumental and very obscure work, Critique of Pure Reason, which was published in 1781. He called these questions antinomies, that is, contradiction of pure reason, because he felt that there were equally compelling arguments for believing the thesis that the universe had a beginning and the antithesis that it had existed forever. His argument for the thesis was that if the universe did not have a beginning, there would be an infinite period of time before any event which he considered absurd. The argument for the antithesis was that if the universe had a beginning, there would be an infinite period of time before it. So why should the universe begin at any one particular time? In fact, his cases for both the thesis and the antithesis are really the same argument. They're both based on his unspoken assumption that time continues back forever, whether or not the universe had existed forever. As we shall see, the concept of time has no meaning before the beginning of the universe. This was first pointed out by St. Augustine. When asked, what did God do before he created the universe? Augustine didn't reply. He was preparing hell for people who asked such questions. Instead, he said that time was a property of the universe that God created, and that time did not exist before the beginning of the universe. When most people believed in an essentially static and unchanging universe, the question of whether or not it had a beginning was really one of metaphysics or theology. One could account for what was observed equally well on the theory that the universe had existed forever, or on the theory that it was set in motion at some finite time in such a manner as to look as though it had existed forever. But in 1929, Edwin Hubble made the landmark observation that wherever you look, distant galaxies are moving rapidly away from us. In other words, the universe is expanding. Now, this means that at earlier times objects would have been closer together. In fact, it seemed that there was a time about 10 or 20,000 million years ago when they were all at exactly the same place, and when, therefore, the density of the universe was infinite. This discovery finally brought the question of the beginning of the universe into the realm of science. Hubble's observations suggested that there was a time, called the Big Bang, when the universe was infinitesimally small and infinitely dense. Under such conditions, all the laws of science and therefore all ability to predict
I'm
the
just
future would
waiting
break
for
down.
all this
If there were
bullshit to get
events
through.
earlier than this time, then they could not affect what happens at the present time. Their existence can be ignored because it would have no observational consequences. One may say that time had a beginning at the Big Bang, in the sense that earlier time simply would not be defined. It should be emphasized that this beginning in time is very different from those that had been considered previously. In an unchanging universe, a beginning in time is something that has to be imposed by some being outside the universe. There's no physical necessity for a beginning. One can imagine that God created the universe at literally any time in the past. On the other hand, if the universe is expanding, there may be physical reasons why there had to be a beginning. One could still imagine that God created the universe at the instant of the Big Bang, or even afterwards, in just such a way as to make it look as though there had been a Big Bang. But it would be meaningless to suppose that it was created before the Big Bang. An expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job. In order to talk about the nature of the universe and to discuss questions such as whether it has a beginning or an end, you have to be clear about what a scientific theory is. Now, I shall take the simple-minded view that a theory is just a model of the universe or a restricted part of it, and a set of rules that relate quantities in the model to observations that we make. It exists only in our minds and does not have any other reality, whatever that might mean. A theory is a good theory if it satisfies two requirements. It must accurately describe a large class of observations on the basis of a model that contains only a few arbitrary elements, and it must make definite predictions about the results of future observations. For example, Aristotle's theory that everything was made out of four elements, earth, air, fire, and water, was simple enough to qualify, but it did not make any definite predictions. On the other hand, Newton's theory of gravity was based.
Okay, guys, so let's discuss this really quick. Let's discuss everything that we heard. Let's try to remember. Let's try to remember most of it. So essentially, time is never ending, and as time goes on, the universe expands, and stars start separating from each other, and galaxies start separating from each other, and we're in this giant empty void in space, right? So yeah, the thing is that you know, I'm just really trying to take it in. I'm trying to think about it because I'm kind of inebriated right now, but it usually comes back to me when I'm sober. But you know, there's different ways of putting this, but let's keep listening because I think we're not far enough into it yet, into this chapter yet, to make any observations. I think it's all been straightforward. It's talking about Isaac Newton and gravity, and how
on an even
and how gravity proves that we're in a solar system.
A simpler model in which bodies attracted each other with a force that was proportional to a quantity called their mass and inversely proportional to the square of the distance between them. Yet it predicts the motions of the sun, the moon, and the planets to a high degree of accuracy. Any physical theory is always provisional in the sense that it is only a hypothesis. You can never prove it. No matter how many times the results of experiments agree with some theory, you can never be sure that the next time the result will not contradict the theory. On the other hand, you can disprove a theory by finding even a single observation that disagrees with the predictions of the theory. As philosopher of science Karl Popper has emphasized, a good theory is characterized by the fact that it makes a number of predictions that could, in principle, be disproved or falsified by observation. Each time new experiments are observed to agree with the predictions, the theory survives, and our confidence in it is increased. But if ever a new observation is found to disagree, we have to abandon or modify the theory. At least, that is what is supposed to happen, but you can always question the competence of the person who carried out the observation. In practice, what often happens is that a new theory is devised that is really an extension of the previous theory. For example, very accurate observations of the planet Mercury revealed a small difference between its motion and the predictions of Newton's theory of gravity. Einstein's general theory of relativity predicted a slightly different motion from Newton's theory. The fact that Einstein's prediction matched what was seen, while Newton's did not, was one of the crucial confirmations of the new theory. However, we still use Newton's theory for all practical purposes because the difference between its predictions and those of general relativity is very small in the situations that we normally deal with. Newton's theory also has the great advantage that it is much simpler to work with than Einstein's. The eventual goal of science is to provide a single theory that describes the whole universe. However, the approach most scientists actually follow is to separate the problem into two parts. First, there are the laws that tell us how the universe changes with time. If we know what the universe is like at any one time, these physical laws tell us how it will look at any later time. Second, there is the question of the initial state of the universe. Some people feel that science should be concerned only with the first part. They regard the question of the initial situation as a matter of metaphysics or religion. They would say that God, being omnipotent, could have started the universe off any way he wanted. That may be so. But in that case, you also could have made it develop in a completely arbitrary way. Yet it appears that he chose to make it evolve in a very regular way according to certain laws. It therefore seems equally reasonable to suppose that there are also laws governing the initial state. It turns out to be very difficult to devise a theory to describe the universe all in one go. Instead, we break the problem up into bits and invent a number of partial theories. Each of these partial theories describes and predicts a certain limited class of observations, neglecting the effects of other quantities or representing them by simple sets of numbers. It may be that this approach is completely wrong. If everything in the universe depends on everything else in a fundamental way, it might be impossible to get close to a full solution by investigating parts of the problem in isolation. Nevertheless, it is certainly the way that we have made progress in the past. The classic example, again, is the Newtonian theory of gravity, which tells us that the gravitational force between two bodies depends only on one number associated with each body, its mass, but is otherwise independent of what the bodies are made of. Thus, one does not need to have a theory of the structure and constitution of the sun and the planets in order to calculate their orbits. Today, scientists describe the universe in terms of two basic partial theories, the general theory of relativity and quantum mechanics. They are the great intellectual achievements of the first half of this century. The general theory of relativity describes the force of gravity and the large-scale structures of the universe, that is, the structure on scales from only a few miles to as large as a million. That's one with 24 zeros after it, miles, the size of the observable universe. Quantum mechanics, on the other hand, deals with a phenomena on extremely small scales, such as a millionth of an inch. Unfortunately, however, these two theories are known to be inconsistent with each other. They cannot both be correct. One of the major endeavors in physics today, and the major theme of this book, is the search for a new theory that will incorporate them both. A quantum theory of gravity. We do not yet have such a theory, and we may still be a long way from having one, but we do already know many of the properties that it must have. And we shall see in later chapters that we already know a fair amount about the predictions a quantum theory of gravity must make. Now, if you believe that the universe is not arbitrary but is governed by definite laws, you must ultimately have to combine the partial theories into a complete unified theory that will describe everything in the universe. But there is a fundamental paradox in the search for such a complete unified theory. The ideas about scientific theories outlined above assume that we are rational beings who are free to observe the universe as we want and to draw logical deductions from what we see. In such a scheme, it is reasonable to suppose that we might progress ever closer toward the laws that govern our universe. Yet, if there really is a complete unified theory, it would also presumably determine our actions. And so the theory itself would determine the outcome of our search for it. And why should it determine that we come to the right conclusions from the evidence? Might it not equally well determine that we draw the wrong conclusions, or no conclusion at all? The only answer that I can give to this problem is based on Darwin's principle of natural selection. The idea is that in any population of self-reproducing organisms, there'll be variations in the genetic material and upbringing that different individuals have. These differences will mean that some individuals are better able than others to draw the right conclusions about the world around them and to act accordingly. These individuals will be more likely to survive and reproduce, and so their pattern of behavior and thought will come to dominate. It has certainly been true in the past that what we call intelligence and scientific discovery has conveyed a survival advantage. It's not so clear that this is still the case. Our scientific discoveries may well destroy us all, and even if they don't, a complete unified theory may not make that much difference to our chances of survival. However, provided the universe has evolved in a regular way, we might expect that the reasoning abilities that natural selection has given us would be valid also in our search for a complete unified theory, and so would not lead us to the wrong conclusions. Because the partial theories that we already have are sufficient to make accurate predictions in all but the most extreme situations, the search for the ultimate theory of the universe seems difficult to justify on practical grounds. It's worth noting, though, the similar arguments could have been used against both relativity and quantum mechanics, and these theories have given us both nuclear energy and the microelectronics revolution. The discovery of a complete unified theory, therefore, may not aid the survival of our species. It may not even affect our lifestyle. But ever since the dawn of civilization, people have not been content to see events as unconnected and inexplicable. They have craved an understanding of the underlying order in the world. Today, we still yearn to know why we are here and where we came from. Humanity's deepest desire for knowledge is justification enough for our continuing quest. And our goal is nothing less than a complete description of the universe we live in. Chapter 2, Space and Time.
So guys, we made it through the first chapter already. And the second chapter is all about space and time. But we learned a little bit about stars and Earth and how the Earth isn't flat and how the Greeks knew a lot about the moon for a very long
We're done. Good work out
time.
there. Party at the clubhouse, cause you're getting
And
paid.
how everything could possibly be in one single atom, and there's infinite stars all across the board, infinite galaxies. We live in a giant void, you know. It mentioned a lot about Isaac Newton and the laws of gravity and polar opposites, and there was a lot that had to do with quantum science, but it was just basics. Quantum science is much more complicated than that. Now, Stephen Hawking was a very inspirational man. Like, when you think about it, like, he kept going. He never gave up. As much pain he was in life, he never gave up. He never listened. He never listened to what anyone else had to say. He just kept it all professional, you know, and everybody was rooting for him. That's the best part of it. He lived such a fulfilling life. He'll be remembered forever, guys. Stephen Hawking will be remembered forever. And I always think, before I complain to my bosses or higher ups, I always think about Stephen Hawking's suffering before I ever feel an inkling sorry for myself. If I ever go through any pain in the future from any stunts, you know, as long as I make it out safely, just know that I won't complain, because Stephen Hawking, you know, he made it through life with one of the worst conditions, and he still exceeded in life as one of the most extraordinary humans to live on planet Earth. Right? Hi, Audrey McCrimmon. Alright, let's keep going to chapter 2.
Our present ideas about the motion of bodies date back to Galileo and Newton. Before them, people believed Aristotle, who said that the natural state of a body was to be at rest and that it moved only if driven by a force or impulse. It followed that a heavy body should fall faster than a light one, because it would have a greater pull toward the earth. The Aristotelian tradition also held that one could work out all the laws that govern the universe by pure thought. It was not necessary to check by observation. So no one, until Galileo, bothered to see whether bodies of different weight did in fact fall at different speeds. It is said that Galileo demonstrated that Aristotle's belief was false by dropping weights from the Leaning Tower of Pisa. The story is almost certainly untrue, but Galileo did do something equivalent. He rolled balls of different weights down a smooth slope. The situation is similar to that of heavy bodies falling vertically, but it's easier to observe because the speeds are smaller. Galileo's measurements indicated that each body increased its speed at the same rate no matter what its weight. For example, if you let go of a ball on a slope that drops by 1 meter for every 10 meters that you go along, the ball will be traveling down the slope at a speed of about 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on, however heavy the ball. Of course, a lead weight would fall faster than a feather, but that's only because a feather is slowed down by air resistance. If one drops two bodies that don't have much air resistance, such as two different lead weights, they fall at the same rate. Galileo's measurements were used by Newton as the basis of his laws of motion. In Galileo's experiments, as a body rolled down the slope, it was always acted on by the same force, its weight, and the effect was to make it constantly speed up. This showed that the real effect of a force is always to change the speed of a body, rather than just to set it moving as was previously thought. It also meant that whenever a body is not acted on by any force, it will keep on moving in a straight line at the same speed. This idea was first stated explicitly in Newton's Principia Mathematica, published in 1687, and is known as Newton's first law. What happens to a body when a force does act on it is given by Newton's second law. This states that the body will accelerate or change its speed at a rate that is proportional to the force. For example, the acceleration is twice as great if the force is twice as great. The acceleration is also smaller the greater the mass, or quantity of matter, of the body. The same force acting on a body of twice the mass will produce half the acceleration. A familiar example is provided by a car. The more powerful the engine, the greater the acceleration. But the heavier the car, the smaller the acceleration for the same engine. In addition to his laws of motion, Newton discovered a law to describe the force of gravity, which states that every body attracts every other body with a force that is proportional to the mass of each body. Thus, the force between two bodies would be twice as strong if one of the bodies, say body A, had its mass doubled. This is what you might expect because one could think of the new body, A, as being made of two bodies with the original mass. Each would attract body B with the original force. Thus, the total force between A and B would be twice the original force. And if, say, one of the bodies had twice the mass and the other had 3 times the mass, then the force would be 6 times as strong. One can now see why all bodies fall at the same rate. A body of twice the weight will have twice the force of gravity putting it down, but it will also have twice the mass. According to Newton's second law, these two effects will have exactly the ability to cancel each other, so the acceleration will be the same in all cases. Newton's law of gravity also tells us that the farther apart the bodies, the smaller the force. Newton's law of gravity says that the gravitational attraction of a star is exactly 1/4 that of a similar star at half the distance. This law predicts the orbits of the Earth, the Moon, and the planets with greater accuracy. If the law were that the gravitational attraction of a star went down faster with distance, the orbits of the planets would not be elliptical. They would spiral into the sun. If it went down slower, the gravitational forces from the distant stars would dominate over that from the Earth. The big difference between the ideas of Aristotle and those of Galileo and Newton is that Aristotle believed in a preferred state of rest, which anybody would take up if it were not driven by some force or impulse. In particular, he thought that the Earth was at rest. But it follows from Newton's laws that there is no unique standard of rest. One could equally well say that body A was at rest and body B was moving at constant speed with respect to body A, or that body B was at rest and body A was moving. For example, if one sets aside for a moment the rotation of the Earth and its orbit around the Sun, one could say that the Earth was at rest and that a train on it was traveling north at 90 miles an hour, or that the train was at rest and the Earth was moving south at 90 miles an hour. If one carried out experiments with moving bodies on the train, all Newton's laws would still hold. For instance, playing ping pong on the train, one would find that the ball obeyed Newton's laws just like a ball on a table by the track. So there's no way to tell whether it is the train or the Earth that is moving. The lack of an absolute standard of rest meant that one could not determine whether two events that took place at different times occurred in the same position in space. For example, suppose our ping pong ball on the train bounces straight up and down, hitting the table twice on the same spot, 1 second apart. To someone on the track, the two bounces would seem to take place about 100 meters apart, because the train would have traveled that far down the track between the bounces. The non-existence of absolute rest, therefore, meant that one could not give an event an absolute position in space, as Aristotle had believed. The positions of events and the distances between them would be different for a person on the train and one on the track, and there would be no reason to prefer one person's position to the other's. Now, Newton was very worried by this lack of absolute position, or absolute space as it was called, because it did not accord with his idea of an absolute God. In fact, he refused to accept absolute space, even though it was implied by his laws. He was severely criticized for this irrational belief by many people, most notably by Bishop Berkeley, a philosopher who believed that all material objects and space and time are an illusion. When the famous Dr. Johnson was told of Berkeley's opinion, he cried, "I refute it thus," and stubbed his toe on a large stone. Both Aristotle and Newton believed in absolute time. That is, they believed that one could unambiguously measure the interval of time between two events, and that this time would be the same whoever measured it, provided they used a good clock. Time was completely separate from and independent of space. This is what most people would take to be the common sense view. However, we have had to change our ideas about space and time. Although our apparently common sense notions work well when dealing with things like apples or planets that travel comparatively slowly, they don't work at all for things moving at or near the speed of light. The fact that light travels at a finite but very high speed was first discovered in 1676 by the Danish astronomer Ole Christensen. He observed that the times at which the moons of Jupiter appeared to pass behind Jupiter were not evenly spaced, as one would expect if the moons went around Jupiter at a constant rate. As the Earth and Jupiter orbit around the Sun, the distance between them varies. Ole Christensen-Rumohr noticed that eclipses of Jupiter's moons appeared later the farther we were from Jupiter. He argued that this was because the light from the moons took longer to reach us when we were farther away. His measurements of the variations in the distance of the Earth from Jupiter were, however, not very accurate, and so his value for the speed of light was 140,000 miles per second, compared to the modern value of 186,000 miles per second. Nevertheless, Rumohr's achievement is not only proving that light travels at a finite speed, but also in measuring that speed was remarkable, coming, as it did, 11 years before Newton's publication of Principia Mathematica. A proper theory of the propagation of light didn't come until 1865, when the British physicist James Clerk Maxwell succeeded in unifying the partial theories that up to then had been used to describe the forces of electricity and magnetism. Maxwell's equations predicted that there could be wave-like disturbances in the combined electromagnetic field, and that these would travel at a fixed speed, like ripples on a pond. If the wavelength of these waves, the distance between one wave crest and the next, is a meter or more, they are what we now call radio waves. Shorter wavelengths are known as microwaves, a few centimeters, or infrared, more than a 10,000th of a centimeter. Visible light has a wavelength of between only 40 and 80 millionths of a centimeter. Even shorter wavelengths are known as ultraviolet X-rays, and gamma rays. Maxwell's theory predicted that radio or light waves should travel a certain fixed speed. But Newton's theory had got rid of the idea of absolute rest, so if light was supposed to travel at a fixed speed, one would have to say what that fixed speed was to be measured relative to. It was, therefore, suggested that there was a substance called the ether that was present everywhere, even in empty space. Light waves should travel
now
through the
they're
ether,
talking
as
about
sound
ether,
waves
which
travel
is
through air,
ancient, which
and their
is
speed should therefore
alchemy,
be relative to the ether.
like what Isaac Newton did.
Different
Isaac Newton
observers,
talked about
moving
ether a lot.
relative to the ether, would see light coming toward them at different speeds, but light's speed relative to the ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit around the Sun, the speed of light measured in the direction of the Earth's motion through the ether, when we were moving toward the source of the light, should be higher than the speed of light at right angles to that motion. That's when we're not moving toward the source. In 1887, Albert Michelson, who later became the first American to receive the Nobel Prize for Physics, and Edward Morley carried out a very successful, careful experiment at the Case School of Applied Science in Cleveland. They compared the speed of light in the direction of the Earth's motion with that at right angles to the Earth's motion. To their great surprise, they found they were exactly the same. Between 1887 and 1905, there were several attempts, most notably by the Dutch physicist Hendrik Lorentz, to explain the result of the Michelson-Morley experiment in terms of objects contracting and clocks slowing down when they move through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in the Swiss Patent Office, Albert Einstein, pointed out that the whole idea of an ether was unnecessary, providing one was willing to abandon the idea of absolute time. A similar point was made a few weeks later by a leading French mathematician, Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regarded this problem as mathematical. Einstein is usually given the credit for the new theory, but Poincaré is remembered for by having his name attached to an important part of it. The fundamental postulate of the theory of relativity, as it was called, was that the laws of science should be the same for all freely moving observers, no matter what their speed. This was true for Newton's laws of motion, but now the idea was extended to include Maxwell's theory and the speed of light. All observers should measure the same speed of light, no matter how fast they're moving. This simple idea has some remarkable consequences. Perhaps the best known are the equivalents of mass and energy, summed up in Einstein's famous equation, E equals mc squared, where E is energy, m is mass, and c is the speed of light, and the law that nothing may travel faster than the speed of light. Because of the equivalence of energy and mass, the energy which an object has due to its motion will add to its mass. In other words, it will make it harder to increase its speed. This effect is only really significant for objects moving at speeds close to the speed of light. For example, at 10% of the speed of light, an object's mass is only 0.5% more than normal, while at 90% of the speed of light, it will be more than twice its normal mass. As an object approaches the speed of light, its mass rises ever more quickly, so it takes more and more energy to speed it up further. It can, in fact, never reach the speed of light, because by then its mass would have become infinite, and by the equivalence of mass and energy, it would have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speeds slower than the speed of light. Only light, or other waves that have no intrinsic mass, can move at the speed of light. An equally remarkable consequence of relativity is the way it has revolutionized our ideas of space and time. In Newton's theory, if a pulse of light is sent from one place to another, different observers would agree on the time that the journey took, since time is absolute, but will not always agree on how far the light traveled, since space is not absolute. Since the speed of light is just the difference it has traveled divided by the time it's taken, different observers would measure different speed for the light. In relativity, on the other hand, all observers must agree on how fast light travels. They still, however, do not agree on the distance the light has traveled, so they must therefore now also disagree over the time it's taken. The time it has taken is, after all, just the light speed, which the observers agree on, multiplied by the distance the light has traveled, which they do not agree on. In other words, the theory of relativity put an end to the idea of absolute time. It appeared that each observer must have his own measure of time as recorded by a clock carried with him, and that identical clocks carried by different observers would not necessarily agree. Each observer could use radar to say where and when an event took place by sending out a pulse of light or radio waves. Part of the pulse is reflected back at the event, and the observer measures the time at which he receives the echo. The time of the event is then said to be the time halfway between when the pulse was sent and the time when the reflection was received back. The distance of the event is half the time taken for the round trip, multiplied by the speed of light. Nowadays, we use just this method to measure distances precisely because we can measure time more accurately than length. In effect, the meter is defined to be the distance traveled by light in 0.00000003335640952 seconds, as measured by a cesium clock. Now, the reason for that particular number is that it corresponds to the historical definition of the meter, in terms of 2 marks on a particular platinum bar kept in Paris. Equally, we can use a more convenient new unit of length called a light second. This is simply defined.
So right now, guys, it's getting into how they measure the speed of light through a certain tool that requires chemicals like magnesium and stuff like that. Whatever it was like mercury kind of chemicals, something like that. But they're talking about the speed of light, all sorts of things. Let's see what chapter we're at. We're at 52. We're gonna listen for 8 more minutes. But I'm taking it in. I'm gonna listen to this again and take it all in for what it is. So I'm gonna hear it twice. You guys are gonna only hear it once, but I'm gonna take it in twice, and I'm really gonna understand. I'm trying to work on multitasking and expanding my brain, but Stephen Hawking definitely is the guy you would choose for this. Now, I'm just gonna go ahead and call it a day. Let me get through this one last thing.
As the distance that light travels in 1 second. In the theory of relativity, we now define distance in terms of time and the speed of light, so it follows automatically that every observer will measure light to have the same speed. By definition, 1 meter per 0.0000000333335640952 seconds. Now, there's no need to introduce the idea of an ether, whose presence anyway cannot be detected, as the Michelson-Morley experiment showed.
So ether
the theory of
cannot be
relativity does,
detected,
however, force us to
and
change
it's the most
fundamentally our
abundant
ideas of space
resource
and
in the entire
time. We must
universe.
accept that time is
Like
not completely
plasma.
separate from and independent of space, but
Right?
is combined with
That's
it
not
to form
pseudoscience,
an
that's
object
real,
called
right?
space-time.
That's
It
what
is a matter of
alchemy
common
taught.
experience that one can describe the positions of a point in space by three numbers or coordinates. For instance, one can say that a point in a room is 7 feet from one wall, 3 feet from another, and 5 feet above the floor. Or one could specify that a point was at a certain latitude and longitude and a certain height above sea level. One is free to use any three suitable coordinates, although they have only a limited range of validity. One would not specify the position of the moon in terms of miles north and miles west of Piccadilly Circus and feet above sea level. Instead, one might describe it in terms of distance from the sun, distance from the plane of the orbits of the planets, and the angle between the line joining the moon to the sun and the line joining the sun to a nearby star such as Alpha Centauri.
Okay.
Even
you gonna
these
help someone?
coordinates would not be of much use in describing the position of the sun in our galaxy or the position of our galaxy in a local group of galaxies. In fact, one may describe the whole universe in terms of a collection of overlapping patches. In each patch, one can use a different set of three coordinates to specify the position of a point. An event is something that happens at a particular point in space at a particular time, so one can specify it by four numbers of coordinates. Again, the choice of coordinates is arbitrary. One can use any three well-defined spatial coordinates and any measure of time. In relativity, there is no real distinction between the space and time coordinates, just as there's no real difference between any two space coordinates. One could use a new set of coordinates in which, say, the first space coordinate was a combination of the old first and second space coordinates. For instance, instead of measuring the position of a point on the Earth in miles north of Piccadilly and miles west of Piccadilly, one could use miles northeast of Piccadilly and miles northwest of Piccadilly. Similarly, in relativity, one could use a new time coordinate that was the old time in seconds plus the distance in light seconds north of Piccadilly. It is often helpful to think of the four coordinates of an event as specifying its position in a four-dimensional space called space-time. It is impossible to imagine a four-dimensional space. I personally find it hard to visualize three-dimensional space. However, it's easy to draw diagrams of two-dimensional spaces, such as the surface of the Earth. The surface of the Earth is two-dimensional because the position of a point can be specified by two coordinates, latitude and longitude. A ray of light from the sun follows the diagonal line and takes 4 years to get from the sun to Alpha Centauri. As we have seen, Maxwell's equations predicted that the speed of light should be the same whatever the speed of the source, and this has been confirmed by accurate measurements. It follows from this that if a pulse of light is emitted at a particular time, at a particular point in space, then, as time goes on, it will spread out as a sphere of light whose size and position are independent of the speed of the source. After 1/1,000,000th of a second, the light will have spread out to form a sphere with a radius of 300 meters. After 2/1,000,000th of a second, the radius will be 600 meters, and so on. It will be like the ripples that spread out on the surface of a pond when a stone is thrown in. The ripples spread out as a circle that gets bigger as time goes on. If one thinks of a three-dimensional model consisting of the two-dimensional surface of the pond and the one dimension of time, the expanding circle of ripples will mark out a cone whose tip is at the place and time at which the stone hit the water. Similarly, the light spreading out from an event forms a three-dimensional cone in the four-dimensional space-time. This cone is called the future light cone of the event. In the same way, we can draw another cone called the past light cone, which is the set of events from which a pulse of light is able to reach the given event. If one neglects gravitational effects, as Einstein and Poincaré did in 1905, one has what is called the special theory of relativity. For every event in space-time, we may construct a light cone, the set of all possible paths of light in space-time emitted at that event, and since the speed of light is the same at every event and in every direction, all the light cones will be identical and will all point in the same direction. The theory also tells us that nothing can travel faster than light. This means that the path of
How do
any
you get
object
out of
through
here?
space and time must be represented by a line that lies within the light cone at each event on it. The special theory of relativity was very successful in explaining
Oh,
that
here
the
it
speed of
is.
light appears the same to all observers, as shown by the Michelson-Morley experiment, and in describing what happens when things move at speeds close to the speed of light. However, it was inconsistent with the Newtonian theory of gravity, which said that objects attracted each other with a force that depended on the distance between them. This meant that if one moved one of the objects, the force on the other would change instantaneously. Or, in other words, gravitational effects should travel with infinite velocity instead of at or below the speed of light, as the special theory of relativity required. Einstein made a number of unsuccessful attempts between 1908 and 1914 to find a theory of gravity that was consistent with special relativity. Finally, in 1915, he proposed what we now call the general theory of relativity. Einstein made the revolutionary suggestion that gravity is not a force like other forces, but is a consequence of the fact that space-time is not flat, as had been previously assumed. It is curved or warped by the distribution of mass and energy in it. Bodies, like the Earth, are not made to move on curved orbits by a force called gravity. Instead, they follow the nearest thing to a straight path in a
Someone
curved
put a
space, which
bounty
is called
on
a
me.
geodesic. A geodesic is the shortest or longest path between two nearby points. For example, the surface of the Earth is a two-dimensional curved space. A geodesic on the Earth is called a great circle and is the shortest route between 2 points. As the geodesic is the shortest path between any 2 airports, this is the route an airline navigator will tell the pilot to fly along. In general relativity, bodies always follow straight lines in 4-dimensional space-time, but they nevertheless appear to us to move along curved paths in our 3-dimensional space. This is rather like watching an
love
aircraft
these
flying over
nice
hilly
cars.
ground. Although it follows a straight line in 3-dimensional space, its shadow follows a curved path on the 2-dimensional ground. The mass of the sun curves space-time in such a way that although the Earth follows a straight path in 4-dimensional space-time, it appears
There's
to
a nice
us
car. I'm
to
gonna
move
take
along
that
a
car.
circular
Screw
orbit
it.
in 3-dimensional space. In fact, the orbits of the planets predicted by general relativity are almost exactly the same as those predicted by the
Sorry.
Newtonian theory of gravity. However, in the case of Mercury, which being the nearest planet to the Sun,
Look at how
feels
beautiful
the
this thing
strongest
is.
gravitational effects and has a rather elongated orbit,
This is
general relativity
Rockstar,
predicts
dude.
that the long axis of the ellipse
This is
should
totally
rotate about the
Rockstar. Which,
Sun
by
at
the
a
way,
rate
I'm
of about 1
listening.
degree in
I'm
10,000
listening.
years. Small though this effect is, it had been noticed before 1915 and served as one of the first confirmations of Einstein's theory. In recent years, the even smaller deviations of the orbits of the other planets from the Newtonian predictions have been measured by radar and found to agree with the predictions of general relativity. Light rays, too, must follow geodesics in space-time. Again, the fact that space is curved means that light no longer appears to travel in straight lines in space. So general relativity predicts that light should be bent by gravitational fields. For example, the theory predicts that the light cones of points near the Sun will be slightly bent inward on account of the mass of the Sun. This means that light from a distant star that happened to pass near the Sun would be deflected through a small angle, causing the star to appear in a different position to an observer on the Earth. Of course, if the light from the star always passed close to the Sun, we would not be able to tell whether the light was being deflected or if instead the star was really where we see it. However, as the Earth orbits around the Sun, different stars appear to pass behind the Sun and have their light deflected. They therefore
Nice.
change their apparent position relative to other stars. It is normally very difficult to see this effect because the light from the Sun makes it impossible to observe stars that appear near to the Sun in the sky. However, it is possible to do so during an eclipse of the Sun when the Sun's light is blocked out by the Moon. Einstein's prediction of light deflection could not be tested immediately in 1915 because the First World War was in progress, and it wasn't until 1919 that a British expedition observing an eclipse from West Africa, showed that light was indeed deflected by the sun, just as predicted by the theory. This proof of a German theory by British scientists was hailed as a great act of reconciliation between the two countries after the war. It is ironic, therefore, that later examination of the photographs taken on that expedition showed the errors were as great as the effect they were trying to measure. Their measurement had been sheer luck, or a case of knowing the result they wanted to get, not an uncommon occurrence in science. The light deflection has, however, been accurately confirmed by a number of later observations. Another prediction of general relativity is that time should appear to run slower near a massive body like the Earth. This is because there is a relation between the energy of light and its frequency, that is, the number of waves of light per second. The greater the energy, the higher the frequency. As light travels upward in the Earth's gravitational field, it loses energy, and so its frequency goes down. This means that the length of time between one wave crest and the next goes up. To someone high up, it would appear that everything below, down below, was taking longer to happen. This prediction was tested in 1962 using a pair of very accurate clocks mounted at the top and bottom of a water tower. The clock at the bottom, which was nearer the Earth, was found to run slower in exact agreement with general relativity. The difference in the speed of clocks at different heights above the Earth is now of considerable practical importance with the advent of the very accurate navigation systems based on signals from satellites. If one ignored the predictions of general relativity, the position that one calculated would be wrong by several miles. Newton's laws of motion put an end to the idea of absolute position in space. The theory of relativity gets rid of absolute time. Consider a pair of twins. Suppose that one twin goes to live on the top of a mountain while the other stays at sea level. The first twin would age faster than the second. Thus, if they met again, one will be older than the other. In this case, the difference in ages will be very small, but it would be much larger if one of the twins went for a long trip in a spaceship at nearly the speed of light. When he returned, he would be much younger than the one who stayed on Earth. This is known as the twins paradox, but it is a paradox only if one has the idea of absolute time at the back of one's mind. In the theory of relativity, there is no unique absolute time, but instead, each individual has his own personal measure of time that depends on where he is and how he is moving.
Sorry, guys.
Before 1915, space and time were thought of as a fixed arena in which events took place, but which time, one will be old on the idea of absolute position in space. The theory of relativity gets rid of absolute time. Consider a pair of twins. Suppose that one twin goes to live on the top of a mountain while the other stays at sea level. The first twin would age faster than the second. Thus, if they met again, one will be older than the other. In this case, the difference in ages will be very small, but it would be much larger if one of the twins went for a long trip in a spaceship at nearly the speed of light. When he returned, he would be much younger than the one who stayed on Earth. This is known as the twins paradox, but it is a paradox only if one has the idea of absolute time at the back of one's mind. In the theory of relativity, there is no unique absolute time, but instead, each individual has his own personal measure of time that depends on where he is and how he is moving. Before 1915, space and time were thought of as a fixed arena in which events took place, but which was not affected by what happened in it. From heights above the Earth is now of considerable practical importance with the advent of the very accurate navigation systems based on signals from satellites. If one ignored the predictions, consider a pair of twins. First twin older than larger. When he returned, as the idea of there is no that depends before 19.
All right, guys. So we have this. We're gonna put 10550 in in the description, because that's where we're at. But I'm gonna bookmark this book summary because I'm gonna read this. But I'm gonna call it a night. I'm very grateful for everything. I'm gonna review this and try to and look at the book summary and study this book more. But I'm getting the grip of it. Uh, I love Stephen Hawking. He's incredible. I'd love to meet his immediate circle. Yeah, whenever sacrifice is brought up in the science community, everyone immediately thinks of people like Stephen Hawking. So take that for what you will. Be very grateful for what you got. And I will see you all later.